Hello and welcome to part two of this series where we're looking at the build of this variable power supply, this 340 volt power supply. And first of all, I'm absolutely blown away by the feedback I've had and reception of for part one. A lot of views, a lot of comments. I wasn't expecting that. I really do appreciate it, and I've got to take a lot of those comments on board really for safety reasons and also to clarify some of the things I'm doing. First of all, I did get the terminology wrong. It's not a regulated power supply, it's a variable power supply. And I think it's worth carrying on with the build as planned, really just to show how this sort of power supply behaves under load. I do need to clarify that before part one I'd actually built the prototype, but I do want to incorporate some changes as we go along. And I think there'll be a third part as well where I'm going to redesign the thing, because some of the suggestions have been fantastic in terms of getting the controls off high voltage and making a low voltage control using some extra components. And I think I want to look at that capability, but I'm not there yet. There were some other suggestions about how to get better smoothing, and I will incorporate those in this particular video. But there are some safety issues. Somebody quite rightly highlighted that one of the 4mm binding posts was probably not rated to the right voltage, and in fact it was rated to 125 volts, so that needs to be replaced, and I have replaced that with something that's rated at 500 volts. And it's worth noting that the prototype board I'm using is 500 volt rated, and the cable I'm using is 1 kilovolt rated as well. So got to make sure those things are safe with this particular power supply. So we'll carry on with the build as is, but then I'll explain some of the modifications that I want to do. I do want to build a PCB eventually, and with the final power supply, and it may well be a regulated one. I've still got some concerns, or I'm not totally convinced about this transformer as well, and you'll see further down the line what I mean by that. So there's quite a bit to do, and let's push on with the build now, and we'll see where we'll get to, and we'll do some deeper analysis of what I've got and look at the test results.
Okay, so let's run through the schematic as we have it. So I've got a fuse in line there, which is at the moment about 250 milliamps. May reduce that if I turn down the current limiting. I've got a double pole single throw switch in place there, and that switch is integrated into the potentiometer. It's a very high quality new old stock potentiometer, so I'm happy to use that switch. And into the full wave rectifier, these 1N4006 diodes are 800 volt diodes. Looking down at the heater winding, I've got an LED there to indicate that the device is on, and that's current limited with a 680 ohm resistor. Into the capacitor, the smoothing filter capacitor, that's 220 microfarads at 450 volts, and I've got this 500k pot. This resistor here, R1, is a current limiting resistor just to protect the MOSFET and all these units that are discharging. The MOSFET itself is an IRF 840, which is very popular or very common MOSFET that can pass or drop 500 volts, so ample specification there. And it can also dissipate 125 watts of power. So as long as that's sitting on the heatsink, that's more than capable to do the job. And it's just a 12 volt Z diode there. Into the current limiting resistor, that's just a common BC547. Pretty much any NPN transistor or general purpose transistor can do that job. I've got a 6.8 ohm resistor there, which will limit the current to about 100 milliamps. And I've just finished off the circuit with a current meter and a voltmeter there as an indicator. And that's what we're going to go with for the moment. What I would like to do is put the prototype on strip board. I do have some quality strip board, which is rated at 500 volts. So again, it's adequate to do the job. what I want to do is put as much space between the high voltage rail and ground, as much space as possible, not really on adjacent strips. And I tend to use a drawing package, just a standard drawing package, to lay out the components. I'd give myself as much space as possible. I do want to transfer this to a dedicated printed circuit board when we've got the final design, and I'm giving myself a large area to modify the design if I need to and put extra components in. So big area, so using all the strip board, keep it spaced out as much as possible, and that's what I'll be doing. And let's get on with the construction.
Okay, so this is where I'm at with the project. I've been away from it for a couple of weeks, been very busy at work, and also kind of a little bit overwhelmed thinking through all the engineering I need to do to the case to make a nice project. Like every large task, I'll just break that down into small component parts and tackle each one at a time. So I'm ready to do that. So this is the enclosure. It's not the highest quality enclosure, but I had to make some compromises with the price, really. All metal cases were extremely expensive. This has got a good solid metal chassis, actually, metal panels at the front. I'm not too keen on the plastic frame, but that's the compromise I've had to make, really. I could look for a scrap PSU or something, test equipment with a similar form factor, maybe use the case from that with some new front panels. Handle's a little bit weak. I think I will swap that for something stronger because I think that will probably give out over time. So that's sorted, really. In terms of the components, I'm going to use strip board. I'm not going to make a PCB. I just want to use materials that I've got to hand. That's 500 volt rated strip board, so that's going to be fine. And I've 3D printed a little cradle so that can sit vertically in the case. Another consideration is the heatsink that will sit on the back of the unit. It's quite a large heatsink. I will flash up the calculations for the heatsink. I'm not going to go through them, but to give you an idea, I've got to keep that MOSFET below 150 degrees, but I really don't want it running anywhere near that. If I'm dropping about 300 volts and drawing 100 milliamps, which I don't anticipate I will, then I need a heatsink that's going to dissipate about 2 Celsius per watt of power. Now that is quite a large heatsink for a T220 case or packaging. So this is actually a lot larger heatsink, so this should do the job very well. But obviously I will be monitoring the voltage drop, and I will be monitoring the current draw when I use the power supply. And if it's operating at that full power for very long, I will kind of ramp it down a little bit, turn it down a bit. I don't think I will be dropping that amount of voltage much because it's designed to be high tension PSU, not a 30 volt PSU. The other thing I need to do is mount the transformer, and I've just got some right angled aluminium on its way, and I think that'll be my next job, really. I don't want to get on with the electronics at this point in time. I want to get the transformer mounted, really, and because then it's in a position to test the electronics as well, because I want to test it before I put anything in the case as well. So lots to do, and let's just get on with it. Okay, so this is where I am with the build of the power supply. What I've done, I've wired up the transformer. I've actually built this frame for it. I'm not very good at metalwork, so I've just used some right-angled aluminium and pot riveted it together. It's quite a strong frame. So it's all been connected into the mains. I do have a variac and dim bulb on the system as well. I have actually tested it because according to the manufacturer's data sheet, I'd needed to do some reforming of the capacitor. It had been stored for a while, so I have brought this up slowly. But the dim bulb and variac are there in case there was any short circuits, and it's good practice to do. So it's a good point to talk about safety. large voltages here, 340 volts in excess of that. So I've wired up the multimeter, so there's actually no hands in the system at all. It's very important to just keep everything away and keep it as safe as possible. So what I'm going to do now is just bring it up. I just want to make sure that this is working. What I've done, I've built the full wave rectifier. I've got the capacitor in place for smoothing. And very importantly, I put a resistor across the capacitor, tacked one in place where the meter is actually as a bleed resistor to make sure it discharges when I've finished doing the testing. So all I'm going to do is bring up the system slowly. Everything is on in place, so it's just a case of bringing up the variac. And I'm bringing that up to 40. And again, about 60 volts DC, which is about right. So I just want to make sure I can bring this up. So that's 100 volts AC, and that's converted to 148 volts DC. And because I know this works, I'm fairly confident in being quick and bringing it up to 240 volts. That's at 200 volts. Let's just bring it around to 240. And there we are at 240. And yeah, I probably need to measure that 100% accurately, but we predicted about 342 volts and we're about 146 volts. So that is working. I've also got an LED in the system, which you can probably just see lit. That's on the heater winding, and that's just to indicate that the power's on. So that's doing okay. Okay, well, I'm ready to test the circuit. I've built it now, obviously, and what I've done, I've just tacked a resistor across the output there as a load. That's a 220 kilo ohm resistor. It's a 2-watt resistor, but that'll dissipate about half a watt at 340 volts. I don't technically need it, but actually I might keep that in permanently just to help discharge things. Obviously, I can turn the voltage down. Anything I can touch is pretty well enclosed, really. I don't want my fingers anywhere near that. And obviously, I've put the MOSFET on a heatsink. What I'm going to do now, I've actually turned this up to full. And I'm just going to turn things on. I've still got the variac and dim bulb in circuit. And I'm going to bring things up slowly and just monitor the output. I've got the current here being monitored, and I've got the voltage here. So that load, as it is, will account for about 1 milliamp. So that's what I'm looking to see. So let's just turn it on and turn the voltage up. So bring things up. Oh, I haven't turned it on. Let's try again. So just bring things up. That's up to, yeah, that's not looking too bad. That's up to 20 volts AC. So I'm going to bring this up to 60. What I'll do, I'll just test this now, see if that works. Let's bring the voltage down to 0. So that'll be dissipating quite a lot of power over that MOSFET. Nothing on the dim bulb, but I'm only at 60 volts AC. The output DC is looking pretty good. Brings up to 120. No smoke, that's good. So bring up to 200 volts. And let's bring up to 240 now. So that's running at full potential. I'm on the dim bulb, obviously, so yeah, 341 volts is what I'm getting at 240 volts, so that's pretty good.
You'll notice I was a fair bit cautious about putting my hands on the control there, and he did that at very low voltage. And what I decided to do was actually control the voltage going into the system using the variac, so I could test it at full mains voltage then. That means there was no hands in the system at all. I quickly decided to fully enclose the potentiometer so that no hands could get near it, and I was then able to test the system fully. What I did then was acquire some 2 kilo ohm 50-watt resistors to test the system under various low conditions and the current limiting as well. What I did notice was that the voltage was dropping, at various loads, and I probably should have done some deeper analysis at that point. That is a proper behaviour for an unregulated power supply. It will draw down the transformer, and in turn that will obviously reduce the gate voltage going into the MOSFET. But I think there's no real concerns at that particular point whether the transformer was up to the job or not. Probably should have thought a little bit more about it, but at that particular point in time, I decided to push ahead and get the system enclosed and do some further testing at that particular point in time.
So let's have a look at the build so far. Now, this is the build prior to part one of this video, so the changes will be implemented after this, basically, and covered in this part two of the video. So the first thing to notice is the binding posts here for the high voltage. Those are actually, I'll admit it, they're only rated to 125 volts, so they're going to be swapped out with some better binding posts here, which are 500 volt rated. So that's one job that needs to be done. Challenge with this sort of style of case, I think it looks really good, but this powder coating is obviously an insulation, so I've had to make sure that I've taken off the powder coating where I need to earth the case. Also, the front panel and the back panel are kind of isolated from the base and the top of the case with this plastic frame. So it's a bit of a challenge to get all the panels earthed, but I want to make sure that those are safe to use. I've also had to run an earth cable really from the handle as well. So I've still got to add that in, but it's something I need to do. Yeah, so that was one of the challenges. I think it looks really smart. You can see the front. I've got these analog meters there, which I prefer to look at the analog meters. I tend to just design a drill template using a drawing package just to lay everything out, and then use that as the basis to go and do the drilling. Got an on-off switch here. Very nice clunk on that switch because it's a new old stock potentiometer, so the quality is actually really good. Just looking at the back, I'm sure we've got that in camera. So I've got the heatsink on the back, which I had to machine part of that, and I've got the MOSFET actually mounted on the inside of there, so there's a big hole in the back of this panel. Mains inlet, I've got a very solid grommet on there which grips it nicely, just using grommets and mains cable that I have had lying around. Fuse holder as well, and that is I've got a, well, these are just 20 millimeter fuses, and I've got a 500 milliamp fuse in there at the moment. That's actually 250 milliamp fuse in there at the moment. But I'll be looking to probably scale that down to 125 milliamps, and I'll explain that as well. So just looking inside the case, you can see I've got the transformer mounted inside there quite neatly, and I've got the electronics mounted in that little cradle I printed just front of the transformer. It's actually placed a lot of space in there, a lot of room to redesign a PCB when I get to that point finally. And there's a good gap between the instrumentation on the front panel and the rest of what's going on in the case. So actually, in terms of the layout and the way it looks, I just think it's really good. So I'm really pleased with that. What I want to do now is, before doing the modifications, I'll just do some detailed measurements and put them on the video, really just to characterize the behavior of the power supply, and then we'll go from there. Okay, so what I want to do before I do any modifications is to just do some characterization work and look at the voltages under load. I've got this meter obviously monitoring the output, and I've got this meter here which is monitoring the voltage at the drain of the MOSFET. So that's going into the MOSFET. Obviously I've got the existing barn plugs there, but I'm not going to be touching those at all. So I'll turn it on under no load first of all, and we'll just see the effect. And when we put the load on, I'll put the scope on just to investigate the ripple on the power supply as well. So let's just see how we get on. So I'm just going to turn this on now. Obviously, you can see this it's been discharging because I have tested this prior. But let's just turn it on for the moment. You can see that's immediately gone up to 327 volts. And we'll just bring the output up, no load at all. And that pretty much matches the output there. So yeah, I'm getting about 325 volts on that meter. I don't know if you can see that well on the screen, but yeah, I think you can. So yeah, that's it under no load. I think we'll just go ahead and put some load on this now. All right, I'm going to do the same test again. I've got a 6 kilo ohm load on the power supply. Meter resistors there, they're each 50 watts of power dissipation capability. So 6 kilo ohms should draw about 57 milliamps at 340 odd volts. So we'll just see what we've got. I'll just turn the meter on here, turn the power supply on. That's immediately coming up to 320 volts. You can see the current being drawn there now. That's interesting. It's dropping the drain side voltage, but we are taking some load from there now, and we'll let that settle in. Yeah, so it's actually coming in below 300 volts, and we are drawing about 50 milliamps, which is probably about right with Ohm's law. And just turn that down. Yeah, so we are definitely drawing down that transformer. Question is whether it's been drawn down too much. Quite a lot of voltage drop on that transformer, so you need to have a think about that. So seems to be fairly well behaving itself anyway in terms of the current draw and the voltage control. Okay. Right, what I've done now, I've changed the load to just 2 kilo ohms. So at 340 volts, that should draw about 170 milliamps. And obviously I've got this current limited at 100 milliamps. So when I do this test, hopefully we'll see the current limiting kick in. So let's just see how we get on. Again, just coming up to 320 volts. It's come up to 100 milliamps now. And it's just kicked in actually. Not sure why the meter's reading 400 volts. I'm going to bring that down. Yeah, so that's something to think about. Turn it off. But definitely kicked in, but I'm curious why the voltage shot up across the drain side of the MOSFET there. Okay, so I've swapped the meter. I've got this trusty 008 on here, and it's reading a SELI 300 volts with the current limiting kicked in, and I can only put it down to the meter as to why I was reading or seeing 400 volts on the drain side when the current limiting kicked in. I've tried all the meters as well, and they're rock solid. So I've just gone to this analog meter, and it's working perfectly fine. So any ideas why that is? I'll be very interested to know. So I want to get an oscilloscope on this power supply to measure the ripple at the output, and I'm not going to connect my mains powered scope onto this particular unit. Mains power scopes are expensive, and you've got to bear in mind that the ground clip on the probe tends to be connected to the earth, so you need to make sure that all the polarities are aligned with the unit you're testing. I think I'm okay, but I'm not going to take that chance. Also, it's a high voltage system, so people tend to use isolated scopes or differential probes or isolated probes, and I don't have any of that capability. So what I'm going to do, I have a inexpensive battery powered scope, which is fine to do this particular job. What I did with that scope was just measure the electrical noise around the area that I'm testing on, and that was negligible. There was nothing there really. So when I actually did the measurements on the power supply output, I did that at 100 milliamps, which is the maximum current draw, which was drawing about 200 volts. I was measuring 2.8 volts peak to peak. So that's only about 1.4%. So that's really good. Just to stress, that battery power scope can measure with a 10 times probe 400 volts peak and or peak to peak, and the probe is a 600 volt probe. So I'm not going to touch it, but it's okay to do this particular job. So everything was just clamped down, so I wouldn't have to touch the system at all. Actually, so 1.4% is really good. So what I need to do now is just take everything on board, process all the information I've got, and implement the modifications to the power supply. And that's what I'm going to be doing now.
So these are the modifications to the circuit. I've transported myself back in time because I've added a few modifications and taken a few away. So I just want to show you what I've done. There was a good suggestion to put a diode across the LED because the LED is not rectifier and it's just really to protect it from the reverse voltage. So just got a standard 1M4001 in there. Now another suggestion was to place filter capacitors between the gate of the MOSFET and ground. The suggestion was a small capacitor, about 10 nanofarads, and an electrolytic. Now, I was very wary about putting that electrolytic in because it's got to charge through this circuit here and discharge through this resistor down to ground, and that's just going to add lag and delay. I did try a small capacitor, 10 microfarads, and that delay was very evident, so that wasn't good, so that went. And what I found, and you'll see later on, when I had this 10 nanofarad capacitor in, it actually held the voltage high. So when I was under no load and tried to reduce the voltage, it would maintain the voltage until the device was switched off. And I don't really know what the reason is for that, so I'm definitely open to some suggestions there. But nevertheless, that had to go as well for that very reason. The other thing I've done is just obviously change the resistor here to a 10 ohm resistor. That will limit the current to about 70 milliamps. And consequently, I did reduce the current meter to a 0 to 100 milliamp meter, just so it's easier to read.
So changes I've done to the outside are obviously the uprated binding posts. These are 500 volt rated. And I've also changed the meter to a 100 milliamp meter. I wanted to do that because we're now limited to about 70 milliamps. Right, well, I have been testing the current limiting capability. Just wondering if that capacitor across the or between the gate and the ground is actually having an effect, because it's not as clean as it was prior to that capacitor. It seems to be limiting between 40 and 80 milliamps, and it's not a clean cut-in like it was before. So I'll just show you behavior. Let me just bring it up, and we'll get to about 40 milliamps. I've got a 2 kilo load on this. You can see it's kind of going in and out there at that point. And as we go high, it jumps to 80, and then it's back down to 40 again. And it seems to be stable at that. So as we reduce the voltage, we get the reverse behavior there. Now, it may be just a limitation of the design. So I'll need to have a think about that. Probably good reason to go ahead with a redesign of the power supply. Right, well, I've got a 10 kilo ohm load on there which won't bring in the current limit in. What I noticed is this behaviour with the 10 nanofarad capacitor between the gate of the MOSFET and ground. So bring it in, goes up okay, but when I reduce that, it holds the voltage. So something's not right there, and it stays there until I actually turn the system off. Let's just do that again. And take it off. The system's still on, but it's down at 0 volts and it's holding. So that capacitor is having a significant effect. So I'm going to take that out. I'm going to retest the current limit in without that capacitor. Okay, so I've taken that capacitor out. Let's just do the 10 kilo ohm test. And it's going up quite smoothly there, behaving a lot more smooth now. And it comes down instantly as well. So, don't know why that is, but that capacitor is definitely having a negative effect there. What I'll do now is just retest the current limit. Okay, back down to 2 kilo ohms, and let's just see what we get now. Coming up to 40 milliamps. Very smooth operation. 60 milliamps, which is the theoretical cutoff, and well, 68 milliamps. Oh, it seems to be behaving very smoothly. Getting instant responses there. Yep, to me that looks a lot better. Well, I think that's it for part 2, and honestly, I've taken this design, I think, as far as I can, and I've taken on board some of the ideas, explored them, haven't quite worked out, and I've taken it back a little bit. I think I've seen enough, though, to want to go ahead and design something that's better. Someone mentioned an LR8 regulator. Sounds really fascinating. I think I do want to go down the regulated route. I want to get the controls on low voltage. But what I will do with this unit, I will do some work with it, and just to see what currents I'm actually drawing, the use cases, and apply it to what do I actually need. Also want to gain some confidence in a transformer as well. So I think we're good. I've enjoyed this process. I've enjoyed all the feedback, and onwards and upwards to the next stage. So if you do like these videos, don't forget to subscribe and like. I really do appreciate that. And in the next few weeks, hopefully, we'll have an updated unit.